Welcome to Think Global Academy. Think Global Academy is an institution organized to train up children from who has finished their junior school level to an entering SS1 to SS3, preparing them to write their WAEC, GC, and JAM as well. And then this institution prepared for the children to take them higher and make sure they are doing very well. I'm Fred Mark, as my name, and I'll be taking you physics. Now, in the junior secondary, we have been taught basic science. Basic science comprises of chemistry, physics, and biology. So in SS1, it's no longer going to be basic science, it's now chemistry, physics, biology, and I'll be taking you the physics aspect of science. So I'll be teaching you physics. Now, let's start. Physics is, by definition, is the study of matter in relation to its energy. The study of matter in relation to its energy. And you have been taught in your junior secondary that matter is anything that has weight and can occupy space. So in other words, everything that is in this universe has mass and is occupying space. As small as this matter is, it has weight, it has mass, and is occupying space. So this matter is an example of matter. So how this matter relates to its energy is what this is all about. Now, physics also, why do we have to study physics? Is to understand the universe and to explore more. That is the aim. Now, let's now go to why a student, why is it important to me as a student? And for those of us who want to study medicine, those who want to study engineering and any other science subject like biochemistry, medical biochemistry, nursing, whether it be control engineering and maybe computer science, cyber security, Microsoft engineering, what is trending now. Physics is very, very important, but we have the basics. So we are going to be starting from the foundation of what physics is all about. I'll be talking about units and measurement. And measurement is all about communication. The scientists use this unit for communication, engineers use it for communication, and even the society. Now, in the society, in this world, basically, we use measurement for business transactions. And then for the engineers, they use them for practical ends. And then for the scientists, they use them to understand natural phenomena. That's what measurement is all about. And now this measurement is very, very paramount in physics. Now there is no law, and there is no science outside measurement that is being quantified. Now, I want to go more detail. Now, everything in life, as far as matter is concerned, has specific measurement. And without this measurement, there is no physics. Now, that leads us to what the unit is all about. Like every parameters, should I put the word parameter, has its own specific unit. Take for instance distance. Distance, I'm going to be moving from point A to point B. It has a unit. The length of that point is, okay, let's say moving from point A to point B. That is the distance. Now, distance from A to B has to be, there's a unit for it. It could be in centimeters, it could be in meters, it could be in kilometers, as the case may be. Now, this is not the unit of distance. Now, that leads us to fundamental quantities and fundamental units. In other words, fundamental quantities and fundamental units. Now, we have three most important basic quantities in physics: mass, length, and time. Mass, length, and time. Now, these are the three most important basic quantities in physics, and these quantities are referred to as fundamental quantities. Fundamental fundamental quantities. Fundamental quantities. Beautiful. Fundamental quantities. Now, fundamental quantities are quantities that depend on themselves for their derivation. Just as we is fundamental, the primary, the smallest, the simplest from the foundation, the basic principles, the basic quantities in physics are mass, length, and time. And their units are also called fundamental units. Units of mass, length, and time are called the fundamental units. So any units, any quantities, or any parameter that is on its own, that depends on its own definition, is what we call the fundamental quantity. A very good example is mass, length, time. These are the basic quantities in physics. We also have electric current. Electric current is also fundamental quantity. We also have okay, let me make it bolder so that everybody can see. Okay, it's okay. Fundamental quantity. We have mass, length, time, electric current. We have temperature. We have amounts of substance. These are fundamental quantities, and their units are referred to as fundamental units. Their units are referred to as fundamental units. So fundamental quantities, again, I said, are quantities that depend on themselves or their definition. While fundamental units are the units of the fundamental quantities. Take, for instance, mass. Mass has unit as kilogram. Now this kilogram is the unit for mass. Mass could be measured in grams, mass could be measured in kilogram, mass could be measured in depends on like example, when we say a bag of rice is 50 grams, a bag of beans is 50 kilograms, as the case may be. But that now is also we call the fundamental unit. For the unit, the basic unit for mass is now kilogram. And that's what we call the standard unit or system unit. In some countries, some people believe that their mass could be in grams, some say their own is in gram, kilogram. But this SI unit, the standard unit for mass, is kilogram. In other words, if I have a mass that is in gram, if I have a mass in gram, because the standard unit for mass is kilogram, I have to convert to kilogram. Convert to kilogram. So the SI unit for mass is kilogram. System units. The SI means system unit or standard unit. The standard unit for mass is what? Kilogram. Another fundamental quantity is length. Length could be in centimeter, length could be in meters, length could be in kilometer, length could be in kilometer, depends. But the standard unit for length is in meters. So meters become the fundamental unit. Length is the fundamental quantity. M becomes the fundamental unit. Unit is now the fundamental unit. Length is the fundamental quantity. Meters is a fundamental unit. The unit of the fundamental quantity is what we call the fundamental unit. So mass could be in centimeter, mass could be in meters, mass could be in millimeters, it could be in kilometer, as the case may be. You could say, I'm running from here to Benin, I'm going from here to Lagos, distance from here to Lagos is 20 centimeters, we say 20 millimeters, we 20 kilometers, depends. Depending on the speed of the car, depending on the speed of the train, or maybe the flight are taking, whatever. But the standard unit for length is in meters. So if I have length in centimeters, if I have length in millimeters, it means I have to convert to length to meters. Because remember I said in physics, measurement is very paramount. There is no law that is visible. There is no science without actual exact measurement. So if there is no measurement, there is no physics. So if length could be in centimeters, length could be in meters, it could be in millimeters, as the case may be. But the standard unit for length is in meters. Is that correct? Okay, now go over to time. Time is also fundamental unit. And the length is a fundamental quantity. Length is a fundamental quantity. And the unit is in seconds. Unit is in seconds. So I will put this one in watts, kilogram. Okay? And moreover, in physics, we use more of symbols. You put it in watts, kilogram. And this one, meters. And this one, seconds. But I prefer you putting it in abbreviation because we deal with symbol as far as physics is concerned. Now, time could be in seconds, time could be in hours, time could be in minutes, but the standard unit for time is seconds. In other words, if I have my time in seconds, it's perfectly okay. If I have my time in hours, if I have my time in minutes, let's say I'm going from here to Benin and I'm moving with a speed of, let's say, 20 kilometers per hour in 20 minutes. That means I have to convert to seconds because the standard unit for time is in seconds. As time goes on, we'll be talking about how to convert from meters to centimeter back to meter. We'll be talking about how to convert from hour to seconds, from minute to second, as time goes on. But for this foundational class, we should know that the standard unit for time is seconds. So if I have my time in minutes, remember I have to convert to seconds. Like say 60 minutes make 1 hour, 60 seconds make 1 minute. And when we get to that time, learn more of it. Electric current is also an example of a fundamental quantity. Now, and the SI unit for electric current is in ampere. Is in ampere. And the symbol for current is I. The symbol for current is I. As time goes on, we will talk about that. So when I see capital M, I'm talking about mass. When I see capital L, I'm talking about length. And when I see time with small t, I'm talking about time. Because capital T means something else in physics. Then I is representing electric current. So when if I want to use the words, I put electric current. But suppose I put I, as a physics student, and I know that once I see I know I'm talking about electric current. But the symbol for electric current is I, and the unit is in ampere. Current is measured in ampere. When I talk about SI unit, I talk about SI, I'm talking about the unit of measurement. Mass is measured in kilogram. Length is measured in meters. So when I say SI units, or when I say units, I'm still referring to the measurement. So mass is measured in kilogram. Length is measured in meters. Time is measured in seconds. Electric current is measured in ampere. Ampere. Temperature is measured in Kelvin. Temperature is another example of fundamental units. And the SI unit is what? Kelvin. Temperature can be in degrees Celsius, it could be in Fahrenheit. As time goes on, we know how to convert from Fahrenheit to Kelvin, how to convert from centigrade Celsius to Kelvin, because temperature could be in Celsius, temperature could be in Kelvin, temperature could be in Fahrenheit, but the standard unit for temperature is Kelvin. So temperature is measured in Kelvin. Then another one is amount of substance, is another example of fundamental quantity, and is measured in mole. Those, when we go to chemistry, and they might express a mole. how things are measured in mole per dm cube, substance, chemicals are measured in mole per dm cube. But as far as unit is concerned, our amount of substance is, the measurement is in mole. So these are basic quantities in physics, and they are called fundamental quantities, and their units are also called fundamental units. And that leads us to what we call derived units. Derived units. Are you following me? Okay? Derived units and derived quantities. I talked about before what fundamental quantity is all about and what their units are called. Their units are called fundamental units. And then we talk about now derived quantities and derived units. Derived units are quantities. Derived quantities are quantities that are derived from fundamental quantities. They are gotten from fundamental quantities, and their definition is from fundamental quantities. That is why it's called derived from. Derived quantities are quantities that are dependent on fundamental quantities for their definition. I repeat, derived quantities are quantities that are derived from fundamental quantities. They depend on fundamental quantities for their definitions, and their units are called derived units. Just like we have fundamental quantities, their units are called fundamental units. The derived quantities units are also called derived units. So quantities that depend on fundamental quantities for their definition, they are gotten from fundamental quantities, are called derived quantities, and they are derived units. Is that clear? Take for instance, for example, volume. Volume is an example of a derived quantity. We have area, we have density, we have velocity, okay? We have acceleration, we have force, we have energy. Let's finish with this. I say quantities, derivation, and units. Now, volume is an example of a derived quantity, and the derivation is length times breadth and times height. Length times breadth times height. That is the derivation of volume, and their units are called, they are in meter cube. Meter cube. Remember, I said that fundamental quantities, the three most important ones are mass, length, and time. Now, everything centered on mass, length, and time. Now, volume is length, breadth, and height. The length of a substance, let's say, for instance, the length of this matter, the width of this matter, and the height of this matter makes up the volume of this matter. The length, the breadth, or other width, and height is what makes up the derivation, makes up the derivation of this matter. And their units are in meter cube because it's mass, length, and time. So, like the length of a thing, if you talk about length of this matter, the width of this matter is still length, is still a meter. Height is still length, is still a meter. So the units are called derived units from fundamental. So, and it is a meter cube. Now, area is also a derived quantity, and it is length times breadth. From the knowledge of mathematics, length times breadth, and their unit is in meter square. Meter square. Meter square is the unit of area. So area is in meter square. Area can also be in centimeter square, as the case may be. But the standard unit for area is meter square. Now, density is also an example of a derived quantity. And the formula is mass over volume. Mass over volume. Mass over volume. Mass, remember, from our fundamental quantity, the SI unit for mass is kilogram. Kilogram over volume is what? Meter cube. Meter cube. Now, in physics, if I reflect this, if I have kilogram over meter cube, it will also be kg per meter cube. So I'm carrying this meter cube up, but this is now the unit of density, kilogram per meter cube. Kilogram per meter cube. Or it could be also kg m3. So these are the same. They are saying the same thing. Mathematically, it's the same. Kilogram from the formula, mass over volume. The mass is in kilogram. Remember from our fundamental quantity. The volume is in meter cube. So if I combine it together, it is not kilogram. I remove now putting minus 3 here and showing that it's going upward, kilogram per meter cube. So the unit of density is kilogram per meter cube. Okay, follow me closely. I think that has to erase so that we can see properly. Velocity. Let's take it one step at a time so that I don't get this. Velocity. Velocity is displacement over time. Over time. Velocity is displacement over time. Time goes on, we look into what velocity is all about. It's the rate of change of displacement with time. The rate of change of displacement with time. Now, velocity is a derived quantity from fundamental quantity, displacement over time, and is now SI is meter per second. So if I do it like this or like this, it's the same. As far as physics is concerned, it's the same. This and this is the same. So the unit of velocity is meter per second. Remember, I said time is in seconds from the fundamental quantity. And the unit of time is seconds, which is m over s. M over s. Displacement is equivalent to distance. Equivalent to distance. Displacement and distance. The difference between displacement and distance is that distance is not specified. Displacement is specified. It's specified. Take for instance, I'm going back to walk 30 meters. Walk 30 meters. There is no direction. So if I say walk 30 meters, do east. That means go to the east and walk 30 centimeters. So speed. Distance is just a space between 2 points. Displacement is now specified. So displacement is equivalent to what? To distance is in meters. And then the SI unit for time is also in seconds. So if I reciprocate and that is turn it upside down or take it upward, it becomes m over s or ms minus 1. So when I see this, I see this, I see this is the same. But to be more accurate, it's better we use this. Just know that the unit of velocity is in meter per second. Meter per second. M over s or ms minus 1. Ms minus 1. So meter per second is the unit for what? Velocity. Another one is acceleration. Acceleration is also a derived quantity. It's change in velocity. Over time. And the unit is meter per second square. change in velocity over time. Change in velocity over time. And velocity is in meter per second. An extra time. Remember, now let me break it down to make it more clearer. Now, change in velocity. Remember, we said velocity is in meter per second. Now, acceleration is change in velocity over time. And the SI unit for velocity, the velocity is meter per second. And then another, okay, let me put it this way. Okay, now, acceleration. We have change in velocity over time. And this is meter per second. That is velocity over s. If this one is meter per second, some of our velocity, which is meter per second, the time is still s because the unit of time is in seconds. So acceleration becomes meter per second. Another s, one more, becomes what? Square. That is s times s. M by s times s, which is ms squared. So the unit for acceleration now is meter per second squared. So acceleration has an SI unit as meter per second squared. And their units are called derived units from fundamental units. Derived units is gotten from fundamental units. So their units are called derived units. So acceleration is now meter per second squared. So let's continue. We have force. Force. Okay. We have force. We have work. We have energy. We have power. So many. And then force is mass times acceleration. Mass times acceleration. And the SI unit is in Newton. Remember, we are dealing with the derived units. What is important in this case is to know their units of these quantities. Knowing the unit of these quantities. Force. Unit of force is in Newton. N. So unit of force is in Newton. But the derivation of force is mass times what? Acceleration. Now, work is also a derived quantity. Force is a derived quantity. Work is a derived quantity. Energy is a derived quantity. Power is also derived quantity. All these are derived quantities, and their units are referred to as what? Derived units. So work is force times distance. Joules. Power is energy. Okay, now force, like I said before, is a derived quantity, and the derivation is mass times acceleration, and the unit is what? In Newton. Work is, the derivation is force times distance, and the unit is in joule. Either you are saying joule or saying Newton meter, because force is in distance is in meters. So if you are saying joules, you are saying meter, you are correct. You are saying the same thing. But the unit of work is in joule. Energy and work is the same. Energy and work have the same derivation and also have the same SI unit. And they are both derived units. Force times distance is a derivation. And they have the same unit as joule. And it's also Newton per meter from the derivation. Force times distance, which is Newton meters. Then we have power. Power is also a derived quantity. And the derivation is work over time. Remember, work is in joules. Work is in joules. Work is in joules. Time is in seconds. So you could say joules, work is over time is power. Work is joule. Time is seconds. So it will not be J1. The other way around. Once it's going up as physics, it becomes S minus 1. So it's joules per seconds, joules per seconds, or watts. Power is measured in watts. Power is also measured in joules per seconds. Joules per second. They are both. Think about those power could be you measure in horsepower, you measure in kilometer per horsepower, you measure in the length of work in power station, say generating, let's say 4,000 watts, 4,000 kilowatts, are all in power. So unit of power is in watts. It could also be in joules per second. So whichever way you are using, you are both correct. Power is in joules per second. Power could also be in watts. So the unit for power is either joules per second or watts. Is that clear? Good. Now let's continue. This we are looking so far is derived units gotten from fundamental units. Derived quantities and derived units, which is gotten from fundamental units. We talk about momentum is also a derived. The pressure, frequency, electric charge, and so on. So many. Momentum is mass times velocity. Pressure, force per area, force over area. Frequency, number of oscillation over time, number of oscillation over time. Electric charge is in coulombs. Now, momentum. The derivation of momentum is mass over velocity. Remember I said momentum, pressure, frequency, electric charge, they are all under derived quantity in its acceleration, velocity, force, pressure, and so on. Power, energy, they are all derived quantities from fundamental quantity. Now, momentum is also an example of a derived quantity, and the derivation is mass over mass times velocity. Mass times velocity is momentum, and the unit is kilogram per meter per second from derived quantities. Now remember, we said mass is in kilogram, velocity is meter per second. So if we combine it together, it becomes the SI unit for momentum. So momentum is measured in kilogram meter per second. Now pressure is force over area. What is force? Force is in Newton. Area is in meter square. So the SI unit, for pressure is Newton meter square, Newton per meter square. Now, if I do something like this, somebody put, okay, now look at area. Area is in meters square. This one is Newton, this one is meter square. But because I'm taking it upward, it becomes Newton meter per Newton meter square. So the minus comes in because it's a division is going upward. So the SI unit for pressure is Newton meter square. Newton per meter square. Newton per meter square. Then we have frequency. Frequency is in hertz. Frequency is in hertz. Or per seconds. Or per seconds. Or per seconds. So the derivation is number of oscillation over time. Number of oscillation over time. So the SI unit is in hertz or per seconds. This is or per seconds. So if you tell me that frequency is measured in per seconds, you are correct. Frequency is measured in hertz, you are correct. But the standard unit for frequency is what? Hertz. Now we have electric charge. Electric charge is in coulomb. Please spell well. Electric charge is in coulombs. Electric charge is measured in coulombs. Electric charge is measured in coulombs. As we proceed, go further, we will talk about what electric charge is all about and how it's being measured. And if there's a conversion, we will learn about it. Okay, in summary of what we have just done today, we started by talking about what physics is all about. And we know that physics is all about what matter, study of matter in relation to its energy. We talk about how everything is matter, anything that has weight and occupies space, and then how these things, how do they relate to energy? That's what physics is all about. And the importance of physics to our generation, to us, is that it helps us to understand the universe and to explore more. And we also talk about how we can able to choose why do we have to do it in school. We talk about that, and then we talk about now went on to our topic, which is unit and measurement. And I told you what measurement is all about. Is basically for communication, for the sciences we use it to understand natural phenomenon. Talk about also how engineers use them for practical ends, and then to the society that use for business transaction. And there is no law and there is no science outside exact measurement. And so we now to talk about that everything practically physics is exact measurement. That is why it is very important for us as physics students to know our measurement. And that leads us to what fundamental quantities and fundamental units. And also derived quantities and derived units. Talk about the difference between fundamental quantities and derived units. And we said derived quantities are gotten from fundamental quantities, and they derive their definition from fundamental quantities, and their units are also called derived units. And then we talk about what fundamental quantities is all about, and we said it's the quantities that depend on themselves for their definition. And we gave what the three most important basic quantities in physics. Take note, we said it is mass, length, and time, but there are also some other quantities that are fundamental, but the three most important basic ones are length, mass, and time, and their units are called fundamental units. And we now talk about the derivation, how we can be able to derive. And as we go on, we now know that measurement is very, very paramount. And in physics, we have the standard units for measurement. Like take for instance length. Length is measured in meters. The standard unit for length is meters. It could be in centimeters, it could be in meters. So if you are going through this video and you do not understand, play back at the beginning and get the full details of this class. Thank you.